Hey, what's going on, folks? It's Mike here, and welcome to the next C in a Day series lesson where we're learning the C programming language. And in this lesson, we're going to be learning about unions. So with that said, unions are a little bit of a mysterious thing in the C programming language. But with that said, I want to go ahead and show you what they are and a few pragmatic examples of where you'd use them. And at this point, we've covered a lot and almost everything as far as the primitives in the C programming language go by the end of this lesson. So with that said, let's go ahead and dive in. So let's go ahead and just start with a definition of what a union is. And I'm going to go ahead and look at the C Unions GNU guide for this. So let's go ahead and just observe what a union is here. So I've highlighted a passage here, and it just states that unions are sort of like structs, but they're a little bit different because all of the members are stored in the same address. So if we recall here how a struct is laid out, I'm just going to write a struct here. It consists of any number of member variables or fields. So this could be things like x here, int y, and so on. But the difference with a union, which I'm going to also label down here, union, and then int x, int y, is how things are laid out in memory. And that's this second passage here. Only one member can be in a union at one time. So a struct is going to look in memory something like this, where it's laid out and you have your x and your y variable. A union itself is only going to have one of these members at any given time. Maybe it's x, maybe it's y, only one at a time. And if I allocate something larger, like let's say I have a long here, this block of memory will be big enough to store at most one and at most the largest element here, a long which could be, say if I put z here, 8 bytes, that's how big this block of memory will be. Now this is a little bit of a weird thing to think about, this data structure that's only one of its elements at one time. So let's go ahead and look at a few examples just so we can understand how a union is working and again how it's different than a struct. So let's go ahead and open up our code editor here. I'll have our main, and let's make this just a little bit bigger for you. How about that size? And let's go ahead and create a union here. So I'm going to use typedef here, and we'll create our new union here. And I'll give the union a name here. Let's just call this example T here for now. Now, normally how I've been using these typedefs here, sometimes I'll also give the name here, but in this case, since I'm giving it the typedef, I can just refer to it as example T below here. Okay, so that'll be a little bit different than what I've done before here. If you want, you can go ahead and give a type here. This just saves me from having to, instead of write union example, I can just write example underscore T anytime I want to use one of these unions. Okay, now let's go ahead and give some different data types here. Maybe a char, maybe an int, and how about a long here? Something like this. So let's go ahead and create our union here. So example T, that'll be the type. And I'll just call it my example. And let's go ahead and see what the size is of this type here. So printf, and we need to use %lu, I believe, size of my example. And let's go ahead and compile this using GCC, our main, and give it an output. And whoops, looks like one mistake here. Forgetting a parentheses, so put that in here. And now we should be good to go. So it compiles, and let's give this a run now. So we're going to see that this takes 8 bytes here. So what's going on here? If we were going to add these up, a character we know takes 1 byte, a integer we know takes 4 bytes, and a long itself is 8 bytes. Well, what if this was a struct, for instance? So let me go ahead and just change this here. Let's go ahead and see what the size is. Now it's probably going to round up, but now we can see it's 16 because we need at least 8 bytes here, another 4 bytes here, and then usually with structures, there's some padding so that we just waste 3 bits here, but this would take 4 bytes here as well. So clearly we can see there's at least some difference structurally in the memory. And again, that's highlighting this difference on the right side where a struct makes room for all of its members, whereas a union just makes room for its largest member here. Okay, so let's go ahead and see how this works here. So I'm going to change this back to a union. And let's go ahead and set one of these fields here. So let's go ahead and say my example.l equals, how about 100, something like that. Okay, and we know what the size is. And let's just go ahead and print off the long value here. So a long value, I believe LD. And we'll do my example.l. And let's go ahead and compile. And oops, this is a LLD. Just giving us a warning there. And if I run this, well, we'll see 8 bytes here. And the value 100 is printed off. Okay, so what happens though if I set this 100 here for the long field, but I try to access our union with the char here? So let's go ahead and just print off what the value would be. A C here, which is a character, so I need to change my format specifier there. And if I run this, well, I get a D. Okay, that's interesting. Let's go ahead and see what happens if I access the I here. Okay, so let's use the %d specifier. I'll change this to I, and I'll go ahead and compile. Compile's fine. And I'll run it, and this time I do get 100. Okay, that seems a little bit more reasonable. But what if I go ahead and change this to, say, a float type here? And I'll need to change my format specifier. So let's go ahead and change this to %f. And I'll recompile, rerun, and, well, this time I get 0, 0, 0, 0, 0. So again, just with this example, we have to think a little bit about what's going on here. If the only thing that I've set here, again, is my example.l equals 100, and I put the L at the end to explicitly say that this 100 is a long type. And when I try to access a field here, or one of the members in this union, if I'm accessing the I here, which is a type of float, then I'm saying, however this value 100L here in my right diagram is stored, interpret those actual bytes, however they are in memory, whatever the binary representation of 100 is, as a float. And floating point numbers have different representations than integer-based numbers like longs. And they're represented as well differently than, say, a char. So let's go ahead and just try to play around with this a little bit more to show some more interesting examples. So for example, let's go ahead and say my example.I equals 3.14, and I'll put an F just to be explicit that it's a float. And let's try to access the character C here. So again, this type here takes 8 bytes, and within those 8 bytes, as many as it needs for a float, which is typically 4 of the bytes, it will set those bytes to store 3.14. Now, whatever happens to be in the rest of those bytes or the rest of the union, well, when we interpret my example.c, that's just going to output maybe garbage to us. But let's go ahead and see with the example. Oh, and I need to change my format specifier here because I'm accessing it as a character. And I'll rerun, and, well, this time I just got nothing or maybe some non-printable character. So we can see how, based off of the context, it matters what or how we're accessing the union. So why might you want to do this? Well, let me go ahead and give you one pragmatic example that's in the real world, and then I'll go ahead and code another example to show you why it might be convenient to structure your data as a union. So what I've done here is I've gone and found a library here that I use or talk about in another series called SDL, the Simple Direct Media Layer. It's a library for programming graphics and multimedia applications in C. And this particular data type that's been defined is called SDL event, and it states here it's a union that contains structures for different event types. Okay, so what would an event be, or an example of an event be in a program? So in this particular library, it can handle things like, did you press your mouse? Did you press a key on the keyboard? Did you move a joystick? And depending on the type of event that happened or was detected, you would want to perhaps do different things. So if we go ahead and look at the actual source code, so if you Google sdlevents.h and you could do a search for union, you'll find that SDL event is in fact a union. And it handles all sorts of different things based off of a context. Again, there's usually only one thing maybe happening at a time when you're pressing a mouse or hitting a keyboard, but you still want to be able to treat or detect those different events here. So you can see that there's all the different events happening here. So this might be an interesting real-world example to look at, and this is often where you'll see it in libraries. Now let's go ahead though and just do another example of where it might be convenient to use a union. And I'm going to change this example just a little bit here. And let's just go ahead and call this union. I'm just going to call it matrix T. And well, what is a matrix? Well, I'm diving a little bit into the math world here. Let me go ahead and get rid of this here. And a matrix, you might remember in some of your classes, is a 4x4 grid here with numbers. And I'm going to go ahead and draw a special one here, which is known as the identity matrix. And these are used all the time to handle transformations in things like computer graphics, as well as they're used to solve linear systems of equations and are often used in machine learning. But if I look at this carefully, this is really just 16 numbers. And I'm going to give them a little bit more specific type here. Instead of just saying numbers, but 16 floats. Okay, represented in this grid. That's a 2D array. Now, oftentimes what I might want to do to represent this is just say, hey, I'm going to have a array of these 16 numbers if this is a 4x4 matrix. So this is 4 rows here and 4 columns on the top. But I'll go ahead and create this as 16 elements here. So let's go ahead and just save this and compile it. And let's just go ahead and see how much memory this takes here. So let's do printf here, and I want to know the size. So that was, again, %ld, size of our matrix T. And you can sort of do the math in your head. 16 floats, 4 bytes per float, means that this is 64 bytes of memory here. Okay, so this essentially looks no different than just creating a struct at this point. But what we might want to do, or where a union can be useful, is sometimes we want to be able to just access one of these rows at a time here, or maybe even one of the columns, depending on if we're row or column oriented. Okay, so the idea would be that we could create another type here, and I'll go ahead and actually create it up here as a struct here, and I'll do a type def. And since there are 4 elements wide, or 4x4 matrix, we're going to have a vector 4. So one of these columns here is really a 4 or a 1x4 matrix. And usually we think of these components as X, Y, Z, and W here. Okay, so let's just go ahead and do our floats, X, Y, Z, and W. And let's go ahead and compile. So nothing strange there. We just have a new struct here. But as I mentioned, wouldn't it be nice if we could address this matrix one vec4 at a time? So in other words, reinterpret this data, the 16 floats here that I have here, which is really just, you know, if I draw this matrix here, is really just 16, or an array of 16 things here, right? So 0, 1, 2, 3, 4, etc. All the different elements that I've stored here. Or rather, I should draw the indices here, and then whatever the elements might happen to be. So 1, 0, 0, 0, 0, followed by 1, etc., etc., etc. Okay? So let's go ahead and add that to our union, so we can address either our union one element at a time or by one row at a time here. So that means I would have a vec4 t, and then I might want to just access one of these columns at a time here. So let me go ahead and just list this out. Now, again, if it's columns or rows depends on your sort of math system, how we're organizing this. So the notation that I'm going to use, I'm just going to say rows here, and we're going to have 4 rows. Okay, so I can recompile this, and it works fine. And let's go ahead and just see this in action by creating a matrix and then printing out the actual rows here. I'm going to make this a little bit bigger just for now, just so we can see all the code on one screen here. So what I'm going to actually want to do here is just create a quick loop here while I is less than 16. And I just want to populate this actual matrix here, all the elements, just so we can see them uniquely here. Okay, so let's go ahead and just create an example matrix. Example. And the first time that we access this, so again, from our union, I'm just going to access the elements at I and just set them to I. Okay, and this should be totally fine. Now, let's just go ahead and access this union again. So this time I'm just going to do a printf here of a float. And let's just go ahead and access these one at a time. So the example rows 0 and do .x. Okay. And let's go ahead and do .y, z, and w here. Okay, so let's go ahead and give this a compile, see if we made any mistakes. Oops, looks like one mistake, copy and paste error. We'll have to add some closing parentheses. And there we go. And now let's go ahead and run this. And now we can see we have 0, 1, 2, and 3 here. Okay, so again, just to illustrate what happened is we initialized our matrix here with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 here. And this all went into a single array. That's essentially just a collection of 64 bytes of information in our actual union. But when we access this by row here, so using this field here, we're instead saying, hey, row 0, just grab the first bytes here, okay? For a vec4, which is the first 16 bytes here. And then we could grab the next ones. That would be row 1, row 2, row 3, etc., etc. Okay, so again, looking at this drawing here, this is row 0. And we've learned about this a little bit in this series previously, and then we'd have row 1, and then, row 2, and then, row 3. These would all be equal size, of course, and so on. But we've learned a little bit about this, just how matrices are laid out. So when we use a union to access the data, or just the bytes stored in this particular data structure, the same holds, that we're just accessing one thing after the other. So again, what's neat about this, with just this little trick here, by using a union, we can access things, whether it's convenient to get a row of information back by just returning the row, or by just storing the actual array. But it doesn't cost us anything from a memory standpoint. This is the same, just 64 bytes of information packed together. So folks, I hope this was useful for you to see how unions are used in the C language. I just showed you a pragmatic example where you might use this to access data in a convenient way, as well as a real-world example where unions are used to handle all sorts of different types of events. I apologize a little bit for my voice. It's a little bit hoarse today as I'm getting over a cold, but I hope you're still able to learn about unions, which are one of the final things that we really need to learn about in the C language. So with that said, folks, I hope you're enjoying the series. I hope you've already liked and subscribed, and we'll see you in the next one.